In this video, we'll be going over the different types of weak bases. So, as the title of the slide implies, there's two types of weak bases. There are amines and there are what are called conjugates of weak acids, or CIBWAs. Conjugate bases of weak acids is what CBWA stands for. So here's an example of a amine. Amines are have nitrogen in it. So it's going to look something like this. It's going to be, or I'll just write some examples here. So like ammonia, so NH3, and just another kind of random example. So methylamine, so CH3 NH2. But the examples of amines, they're gonna have this general form. So they're gonna look like this. So they'll have, like, I'll put R1, R2, and then R3. Okay, and then R represents a side group, but that's generally how they're going to look. That's not what's important about the amine. What's important about the amine is the nitrogen will have three, it's going to make three bonds, one, two, three. But here's what's going to make it a base is it's going to have this lone pair. So it's going to have a lone pair right here. Okay, and this is going to have an affinity for hydrogens on water, and it's going to snatch some hydrogens off of water and make a bond with with that lone pair right there. So I'm kind of going into how it's a base. So it's a base because I'll draw it like this with the correct shape. So I'll put R1, R2, R3, and R just stands for side group. So it could be a C or an H. Okay, and then as we know, the C's can be connected to more C's. But like I was saying, that's not what's important. You'll see that the nitrogen makes three bonds and it has a lone pair. So this lone pair will use its electrons to make a bond with hydrogen on water. So what it does is it rips the H off of water, and it's gonna make a bond. So it's gonna go like this, and then it'll look like this. It'll be like R1, R2, R3, and then it'll have an extra bond here. So that'll be the new bond. So essentially, what it does is it fits the exact description of a Bronsted-Lowry base. It's a proton acceptor. Okay, so how about conjugates of weak acids, CBWAs? So some examples are they're actually salts. So you're gonna see, like, it's the conjugate base of a weak acid. So if you have like HCN, so it's not HCN, of course that's a weak acid. It's its conjugate. So it's HCN, it's CN minus. Okay, or if you have, let's say, hydrofluoric acid, which is HF, so the conjugate of that is F minus. Okay, and the let's just do another one more example. Like acetic acid is C2H3O2H. Or actually, let me put the how should I write that? I'll write it like this: CH3COOH, acetic acid. Okay, the conjugate of that, so that's acetic acid. Its conjugate is the acetate ion. Okay, so these are all weak bases, and they're not going to look like this either. They're going to have usually a group 1 metal that balances this charge. So these are called salts. So like sodium cyanide, or like potassium fluoride, or sodium acetate. Okay, so what these are going to do, how is it a base? So the salt, and salt is generic for an ionic compound, so metal, nonmetal, or metal to a polyatomic ion, as you see here. So it's going to be like sodium cyanide, for example, and this will 100% dissociate. So you have this will be in like crystal form, it hits water and it dissociates into this and this. Okay, now this is going to be very similar to what this does. The cyanide ion is going to look like this. It's going to be a C. Uh, let's see. It's going to have a 1, 2, 3 triple bond, and it's going to have a lone pair there. Okay, so this lone pair, this is the second thing that happens. This lone pair, similar to the amine example, this will has an affinity for hydrogen on water. So like the amine over here, this lone pair is going to snatch an H off of water, and then it'll turn water into hydroxide. So it makes hydroxide indirectly. Okay, so it's a proton acceptor, just like all Bronsted-Lowry bases are. Okay, so and it's so we'll go through a quick reaction of each on the next couple of slides. Okay, so how exactly does it do it? So we're gonna draw to do this correctly. We're gonna have to show a Lewis structure. So I'm gonna draw out Lewis structures of everything here. So I'm gonna write the ammonia, and I'm gonna draw it sideways. I'm used to drawing like group fives. I'm used to drawing them like that, like the trigonal pyramid. But here I'm just gonna draw it sideways because it's easier to demonstrate what happens with the lone pair. And then I'm gonna draw the water's Lewis structure. Okay, it's got these lone pairs here. The oxygen's a 3.5 electronegativity. The hydrogen is a 2.1. So the electrons here are going to be shifted up like that. So they're actually closer to the oxygen. And same thing here. Okay, we have 3.5, 2.1. So these electrons here in that covalent bond, those electrons there are going to be shifted up towards the oxygen. So this oxygen is going to have a slightly it's going to be partially negative. Okay, and the hydrogens are partially positive. So what you're going to see the nitrogen do is going to use these lone pairs, and it's going to make a covalent bond with that hydrogen. And the result of that bond forming is this bond will break, and these electrons will then go to the oxygen, since they're actually kind of close to the oxygen anyway. And I forgot to do a little EN analysis on the ammonia. So nitrogen is 3.0, this is 2.1, so you're going to have dipoles going like that. Okay, so the nitrogen is partially negative, and the hydrogen on the water molecule is partially positive, and this guy's partially negative. So there's an affinity here, there's an attractive force here, so much so that it actually makes a covalent bond. And as we see, it's a weak base, so it doesn't do it, full blown, but it does do it a little bit. So it's going to shift some of this matter will be shifted over here and make these two molecules. So your product is going to be the ammonia ion, so which will look like this. So I'm going to draw my ammonia. The previous example, just to tie this in with the previous example, I was calling this like R1, R2, and I was calling this R3. And the new bond is going to be right here. Let's do it in light blue. So this right here is going to be this brand new bond that forms. Okay, and let's tag this H. Let's make it light blue. So you could see that this is the new bond that formed right here. So this is the new bond that formed. And of course, these electrons, they went over here. So these electrons here from that bond went here to the oxygen. So the oxygen now has an extra set of lone pair electrons, and we'll make those like a green color to represent this arrow right here. Okay, so that is those are the new set of electrons that it got from that covalent bond. Okay, and then this is the hydroxide ion. So if you remember our Kw in the auto ionization of water, this is a this is a base. So it's going to make this number, it's going to drive this number up, and to compensate, this number will go down so that it can retain its equilibrium value for water. So H2O, H3O will be present. It just kind of drops down a lot because it's a basic solution now, and this number will spike up. Okay, and so this number to compensate so that the law of mass action, and so that it can reestablish equilibrium, this number will have to go down. Okay, when this one spikes up because of the base being added. Okay, so that's how it works, how an amine works. Next, we'll go into a conjugate base of a weak acid. So this is kind of a new acronym that I like to use because I don't like writing this out every time. So it's conjugate base of a weak acid, and this is why I've been asking my students to have the 7 strong acids memorized, is because we want to be real fast and quick with the anions of strong acids, because those are not CIBWAs. Those are not conjugate bases of weak acids, like Cl minus, Br minus, I minus, NO3 minus, and what else do we have? ClO3 minus and ClO4 minus. Just wanted to remind you that these are nothing. Okay, nothing, 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 nothing. So conjugate bases of weak acids. So this is going to be stuff like Cn minus, F minus, and this is also why I wanted you guys to get familiar with that list of polyatomic ions I gave you guys, so that we can identify these quickly and know what they're going to do when they interact with water. So like the acetate ion, these are some of the more common ones that we'll come across, or like the nitrite ion, or the SO3 2-misulfite ion, phosphate ion, etc., etc. Okay, so these are all CIBWAs, conjugate bases of weak acids, all of them. And I'll use F minus because it's simple. So again, these are not going to appear like this. They're going to actually, usually you'll see them tied up with a group 1 metal to balance out that charge. So these do not, they don't exist by themselves. Okay, so if you grab a bottle of this, it's going to be mixed with like a group 1 ion, so it's going to look like that. Okay, or like NaF, and similarly with all the others. So here's how it works. It does just like what the last slide was showing on the last slide, is these will also have an extra lone pair. That's why they have that negative charge. So these are going to also have a lone pair, which will have an affinity for the hydrogen on water. Okay, so just like the last slide I was going over, the partial negatives on the oxygen, partial positive here and here. We got some dipoles there. And then this is going to do the same thing as the last slide was showing. So these electrons are going to make a bond with the H, and then these electrons will go to this oxygen weakly, so it'll do it, but not very well, but enough to make it a basic solution. So it's going to make the conjugate, which is actually hydrofluoric acid, and the water then becomes the hydroxide ion. Let's draw out the dot structure, Lewis dot structure. Okay, and we can make this green, these electrons here, to represent these electrons here. Okay, those are the new electrons. So we have our hydroxide. So just like on the last slide I was showing, it makes that teeter-totter for Kw. So here's H3O, and here's OH. So it's gonna make this number go up, and then this number, to compensate and to reach Kw again, this number is gonna have to go down. So, and then we have pHs greater than 7. It depends on your initial concentration of this, of course, and the Kb of this. Okay, it will determine what the pH will be. Okay, so before we go crazy and do all these pH problems and all that, we need to slow down and just make sure we know how to write a dissociation equation for a weak base. Okay, so that's going to be on the next slide. So this is the your turn. It says, for reactions with amines, draw Lewis structures. So I'm asking you to draw a Lewis structure of each reactant and each product. So let me go back a couple slides and show. So I'm asking you to, for the amine reaction, to draw this out. Okay, this whole process. Okay, so on the your turn. So let me actually I wanted to show you one thing with pyridine. It's actually a ring. So it kind of looks like benzene, but in place of one of the carbons, there's a nitrogen there inside the ring. So pyridine looks like this. It looks like this. Let me write the nitrogen there. Okay, it looks like that. And there's alternating double bonds. So there'll be a double bond here, here, and here. Okay, and the important thing again, none of that ring really matters. This is where all the activity happens, is right there in that lone pair. Okay, so and these, make sure you dissociate. 3 and 4 are the salts. So make sure we don't care about the spectators. So make sure you break these up. So this is going to be Cn minus, and then use this. So this is process number 1. Process number 2 is the Cn goes on to interact with water. Okay, so write out the dissociation equation for that one, and for this one also. So do a similar thing for that one. Okay, and make sure you draw the correct shape also. Okay, so you may need to go back and look at your Lewis structures, but remember this is 5A, and don't be intimidated by this. It's just a methyl group. So it's just a C with, it's going to have 3 hydrogens on it, and that carbon is going to be connected to the nitrogen there with 2 H's on the nitrogen. Okay, so remember the general form. Looks like this. Okay, looks like that. Okay, R1, R2, and R3. And these don't really matter. As you see here, even on this ring, this would be like R3, and it actually has a double bond here. So this is like R1 and R2, that double bond right there. Okay, so see if you could use that setup to draw the Lewis structures of this, and this one. All right, so that's the end of our video. See what you guys come up with.